Alright, so for section 4.1, angles and their measures. So we're going to talk about trigonometric functions, and well, you may have seen about this before, how these trigonometric functions are functions mostly of angles, but still, I mean, these angles are still regarded as real numbers anyway. I mean, but the way we have, like, the way we see the reason why we see these trigonometric functions as pretty much as a separate group from the usual group of functions that we deal with usually, it's because of their applications to angle situations and other pretty cool things that we're going to look at. So, well, number one, let's define what trigonometric functions are, and these are functions of an angle. And again, so they relate the sides of a triangle with their angles, and well, so what these functions have in particular, as opposed to other functions such as the radical function or the cubic function, like pretty much all functions from the parent function list. These functions in particular are periodic. We're going to look at those details later. So, but in the meantime, first things first. So, how do we define this angle? Because, well, first we're going to convert, or we're going to look at the way we measure angles, and that is in degrees and radians, and furthermore, degrees can be expressed as decimals and also as degrees, minutes, and seconds. Well, we'll see about all those details. In the meantime, okay, we need to define what a ray is. An array is a portion of a line that starts at a point V on the line and extends indefinitely. That is, starts at this point, extends forever, and starts at the point V. That point V, well, we could have used a different letter, but you'll see why. You'll see why it's going to be the letter V. Well, yes, it's called vertex. That's why. Now, what's the difference between a ray and a segment? A segment, in this case, starts at one point and finishes at another point. So it's a segment that we can measure either with a ruler or whatever it is. And well, so angles are formed when we have the intersection of two rays. So number one, when we have the intersection, so to speak, like this, there's one ray and this is another ray, and both rays have a point in common. That point in common is the vertex, and the gap in between, this one right here, let me show you. So that's this gap right here, or that space, is like the distance between the two, right? But we don't call it a distance. In this case, we call it an angle. And well, usually we measure this angle from an initial side to a terminal side. All right. And well, we use different letters to express angles. Maybe the most common one you might have used is the Greek letter theta. All right. However, we also use other letters such as alpha, beta, gamma, of course, theta, and phi. So alpha and beta, we're going to use them when we look at situations in which we deal with more than one angle, such as the addition, the sine and cosine for an addition of angle, and gamma, alpha, beta, and gamma, as I said, we're going to use them together when we look at the law of sines and law of cosines, because in this case we relate three angles at the same time. And phi, that angle phi, it's a symbol you're going to use when you get to Calculus 3, Math 252, I believe it's here at SGSU. And that's to describe the angle in three-dimensional when you're talking about spherical coordinates. And that's the angle that spans from the positive z-axis to the negative z-axis. Well, you'll see about that when you get to Calc 3, when you get to see all this in 3D. It's pretty cool stuff, by the way. And well, so that's not the only way we can define angle. Check this out. We can still have the same arrangement of rays like this, but instead of going in this direction, like in the direction we went here, we can go about, how about this? Check this out. Start here and end up here, and still this is the initial, and this is the terminal. All right, that's another way to measure angles. I mean, ultimately, well, we're doing some sort of a cycle which is 360 degrees. Well, we're going to define more about that, and well, let's call this alpha, just for the sake of notation. All right, just to give it some name. Let's call this beta, and of course, we can have the same arrangement of rays, and still go from here, from this point, from this initial to this terminal. But check this out. We can go about like this. Right? We can do one whole turn and then go to that terminal side. That's another way to go about from that initial side to that terminal side. All right? And let's call this gamma. Like this, and again, this is still the initial, and this is the terminal side. All right, so that being said, now that we have an idea of how angles are formed and how are they defined, how can we go about them, how about we define angle? So we use the angle theta, the symbol theta, whenever we have an angle in standard position. What do we mean by standard position? So in this case, we call an angle to be in a standard position when we impose a Cartesian plane and our initial side is actually the positive x-axis, and the vertex, that is the intersection between the two rays that form the angle, is the origin in the Cartesian plane, like this. So check this out. So that's going to be, that's the origin. That's always going to be the initial side. The positive x-axis is always the initial side, and then you go anywhere you want from there. Let me go, for example, here. How about that? And well, that's going to do the following. We're going to sweep in the counterclockwise direction. Let's call this theta. Okay, in this case we will call theta for all of them, because theta is the symbol used for all angles that are in standard position. That is, again, when the two rays intersect at the origin by imposing this Cartesian plane. And well, this angle happens to be in the second quadrant. All right. And what else? Of course, we could go about, okay, start at the initial, which is the positive x-axis. We can also go about negative angles in this direction, that is, in the clockwise direction. And check this one out. Notice I'm mentioning here something about quadrantal angle. What is a quadrantal angle? Oh, number one, before looking at quadrantal angles, this angle, this second angle right here, it happens to be in the fourth quadrant. All right. So angles that lie inside a quadrant, well, we just say they're in the first quadrant, the second quadrant, the fourth quadrant, or the third quadrant, whatever they are. However, there's a particular kind of angle called quadrantal angle, and those quadrantal angles are angles that coincide on one of the axes themselves. For example, the 90-degree angle. So the 90-degree angle, it's one of them. And that's an angle that it's neither on the first quadrant nor on the second quadrant. And likewise, The negative x-axis would be an angle that it's neither on the second quadrant nor the third one, and the 270-degree angle, the one pointing down, it's also an angle that it's neither on the third quadrant nor on the fourth quadrant. It's actually on the space right in between, and those we call them quadrantal angles. And for example, we have this this theta to be one of those quadrantal angles. All right. So again, just basic ideas, basic definitions. So special angles called quadrantal versus any other ordinary angle here. All right. Now let's look at other ideas here. So there are 360 degrees in one cycle. You know, just like any other number system. You know, like the decimal system. You know, so we can always divide like 1 centimeter in 10 millimeters, 1 decimeter in 10 centimeters, for example. Well, it turns out that that the circular system has its own division, and in this case, we have 360 units, if we will. You know, like having a pizza, for example, and divide it in 360 degrees. I don't know if that's possible anyway, unless it's like a really big one. But and well, each slice will be 1 degree, right? So and it takes 360 of those units, that is, of those degrees, to complete one cycle or one revolution, either clockwise or counterclockwise. So again, we're going to look at those details. What does that mean to go on the clockwise direction? What does it mean to go in the counterclockwise direction? All right. And well, so one degree is just 1/36, a very tiny portion of a complete circle or a complete revolution. Now, a right angle, on the other hand, is an angle that measures 90 degrees or 1/4 of a revolution. And likewise, a straight angle, it's an angle that measures 180 degrees and or half a revolution. You know, those are the typical angles that we don't call. Sometimes we don't call them by their number of degrees, but rather by what they represent, like a right angle, a straight angle. So it's understood to be a 90-degree angle and a 180-degree angle, respectively. All right. And well, so how about we approximate the location of each angle and identify which quadrant are they in? All right, so 135-degree angle. So in this case, and well, notice I have imposed a Cartesian plane, and I draw this. I put this unit circle, even though we're not going to look at the unit circle just yet. But we will be there eventually. And just to help us go from its initial side, like this, to whatever terminal side. Well, in this case, how about we go from here and rotate? Well, so here is 90 degrees, right? How many more degrees do we need to get to 135? 45, so let's continue 45, which is here right in the middle, right? So that's where our 135-degree angle will be at. And let's call this theta equals 135. And again, we use the symbol theta because we're talking about angles in standard position. That is, when the two rays coincide at the vertex located at the origin of the imposed Cartesian plane. All right? Let's look at the angle negative 120. Well, so notice how we went counterclockwise for positive angles. So for negative angles, we're going to go clockwise. So again, starting at the positive x-axis, and then from there we're going to rotate, or we're going to go around this circle. And well, again, here so far I have 90 degrees. How many more degrees to reach 120? 30 degrees. I'm going to go somewhere like here. all right? And, well, that's going to be from the vertex. So that's our angle. And, well, this arrow to indicate that we're going in the clockwise direction for a negative angle in this case. All right? Now, of course, we need a system to represent these values, just like we have the decimal system, the hexadecimal system, the binary system for other types of number system that we work with. Well, the trigonometric field has its own system, and that's again the degrees. Well, we already have an idea about the degrees, and we know that each unit, each degree represents 1 over 30 over 360th part of the entire revolution. All right, so let's see how we go about it. Well, so we can, those subdivisions, actually those subdivisions can be represented in two different ways, as decimals or like minutes and seconds, like the clock, you know. In the same way, for example, if we have a meter, we can further divide that into what? Decimeters. That's 10 decimeters, and each decimeter can be further divided into 10 centimeters each. Likewise, 1 degree, which is 1 unit, can be further subdivided into 60 minutes, and 1 second is also 60 minutes, which is 1 over 3600 of a degree. Okay, so for example, just to give you an overview of how we represent an angle using all these numbers and all these symbols. So an angle that is 15 degrees with 45 minutes and what's that? 17 seconds is written compactly as 15 degrees. We use the degree symbol. 45, the minute symbol is one quotation mark, and 17 with double quotation marks. That's to denote the seconds. Okay, so now to convert between one system and the other, we need to do some process here. So this is what we do. We're given an angle from degrees, minutes, and seconds. The one is to rewrite it as decimal form. So all we do is write these 3 numbers as a sum of 3 numbers without their symbols, and multiply the minutes by 1 over 60 and multiply the seconds by 1 over 3600. And that's what it's going to give us the result in decimal. To convert the other way around, from decimal to degrees, meters, and second, it's a longer process. So first we need to write the given angle as the sum of an integer and its part, and most likely we'll have to repeat steps 2 and 3, but actually I'd rather see that in action rather than reading the process. I'd rather refer to it when we look at the example. So check this out. Let's convert 45 degrees, 10 minutes, and 15 seconds into decimal form. All right. So first thing we do is write this quantity as a sum of 3 quantities. That is 40 degrees plus 10 minutes. I'm going to leave a space for something, you'll see, and plus 15. And times something. So what are those somethings? So recall that the minutes are multiplied by 1 over 60 to convert those into degrees, and then those seconds, oh, I forgot the second symbol, the double quotation mark, we multiply by 1 over 3600. And let's just punch this in the calculator. So let's run to 4 decimals for now. Let me give you the answer, and then I'll show you how to do this on the graphing calculator. So that's going to give us 45.1708 degrees. Don't forget the degree symbol. We're still in degrees. Later we are going to move on to the conversion between decimals and no, the degrees and radians, and well, this degree symbol will matter depending on what we're working on. All right, how do we do this in the graphing calculator? So nope. Clear all this. So that's going to be 40 plus 10 times 1 over 60 plus 15 times 1 over 3600. Just punch it in the calculator, we should get that result. Okay, 40.1708, rounding to 4 decimal places. The fifth digit is a 3, not big enough to round it up to 9, for example. All right. So this one is fairly easy to do. I mean, it takes only one step, just a multiplication. However, converting between degrees and minutes, and seconds from decimal to degrees, minutes, and seconds, we need to work a little bit more than just that. So number one, okay, so the degrees, okay, let's break this up. Okay, 12.87 degrees. This is the same as saying 12 degrees plus 0.87 degrees. I mean, those degrees are just a decimal. It's like saying 1.5 equals 1 plus 0.5. There's nothing crazy about it. But the thing here is we are going to work on the decimal and write down its equivalent in degrees, because check this out. These 12 degrees are going to remain 12 degrees plus this 0.87 degrees is the same as saying this. Check this out. 0.87 times 1 degree. All right? Either one, like when we were saying percent or decimal, well, so that's how we go about it. Now, what is that going to mean? Because from here, that's when we're going to convert between degrees to minutes, and then we will repeat the process to convert those remaining minutes into seconds if applicable. In some cases, it may not apply, but I chose a particular example in which actually applies. And well, let me highlight this 1 degree, because we are going to write down its equivalent in seconds, because now we're going to go from degrees to, no, not seconds, to minutes. Okay, so this is the same as saying 12 degrees plus 0.87, and 1 degree is the same as saying 60 minutes. All right, and let me highlight the minutes so you can see what am I converting into what. That is the 1 degree and the 60 minutes. All right. So how about we multiply this 0.87 times 60? Multiplying that, it's going to give us, oops, going to give us 12 degrees plus 52.2 minutes. And we're essentially done converting those decimal degrees into minutes. However, we need to repeat this process because what? Because these minutes have a decimal. Whenever we have minutes with remaining decimals, we need to repeat the process. And what I'm going to do, I'm going to break up this decimal number in the same way we did initially. So that's going to be 12 degrees plus 52 minutes plus 0.2 minutes. In the same way that 12.87 degrees is equal to 12 degrees plus its decimal part, same here with the minutes. 52.2 is the same as saying 52 plus 0.2. But now we are going to convert these minutes into seconds. All right, so this is the same as saying, okay, let me write the whole thing. 12 degrees plus 52 minutes plus 0.2. Instead of saying 0.2 minutes, I'm going to say 0.2 1 minute. All right, I'm just going to change the notation in the same way I did it here when I went from, come on. So now we're going to convert this minute, 12 degrees plus 52 minutes plus 0.2 times 1 minute equals 60 seconds. And then let me highlight this. 1 minute equal to 60 seconds. And 12 degrees plus 52 minutes and 0.2 times 60 rather, that's going to give us 12 seconds. And in fact, we're done with the problem because actually these seconds are an integer. In some cases, you may get seconds as a decimal, but in that situation, just round up to the next integer. Either round up or round down. In this case, we got a nice integer at the very end. All we do is simply 12 degrees, 52 minutes, 12 seconds. That's about it. All right. It's not the hardest problem in the world to convert between decimal and degrees, meters, and seconds. It just takes time to write one step and the other. Although if you feel confident on skipping from here to all the way to that step, by all means, just make sure that you know what you're doing. All right. We're going to move on to a different system of measuring angles. In this case, those are the radians. But first, we need to define or to look at some geometry. Well, not yet. Yes, the radians are a different system to represent angles. And well, what is a radian anyway? So, and actually, it's the preferred system used in pretty much calculus, pre-calculus in applications, unless we're using this in applications to like physics, mechanics, or classical mechanics, or mechanical engineering, or the like, in which we need the angles to see actually what's that number rather than radians, So, well, the radian measure is found by finding the ratio of the length of the arc that spans on a circle to its length on the radius. Well, let's draw a picture for that. So, if we have a circle right here, so that's going to be, so it has this radius r, and this is an angle here. This is the arc length right here. That arc length subtended by the two rays on the circle having the center precisely at its vertex. Okay? And the ratio of this arc length S to the radius of that circular sector, that's the that's the angle represented in radians. That's what we call a radian. And by the way, these are unitless. Actually, we don't use any symbol to represent radians as opposed to degrees. We use that little circle there, but not for radians. And the reason why radians do not have any units, that's because these are centimeters, for example, over centimeters, or meters over meter. Those units cancel, they just go away. All right. So from here, well, now that we define these angles in radians, well, so how about we find some arc length? Well, if we solve this formula, theta equals S over R, this S will be equal to R times theta. In other words, we multiply the radius of that circular sector times the angle subtended by the two rays. In this case, it's in radians. So we don't know how to convert to radians yet, but we will soon. So let's look at a very straightforward problem. Find the arc length, or the length of the arc, of a circle of radius 4 meters subtended by a central angle of 0.5 radians. So in this case, we're given radians because we don't know yet how to convert. Well, maybe you know already because you have seen trig before, but at the point right now, We're going to suppose we don't know how to convert those. And well, so S equals to R theta, that is the radius, which is 4 meters, times the angle, which is 0.5. And that's simply 2 meters. Very simple calculation. All right, that's how far it is from, as a picture, if we will, how far is it to go from this to 0.5 radians along this radius to that circular distance. That's our length of the arc, or arc length. All right. Of course, I mean, like we mentioned before, we will be going back and forth between the degree system and the radian system. So there has to be a way to do the conversion, just the same way we convert between meters and centimeters, or kilometers and miles. So we need to find a way to get that conversion. So converting from degrees to radians and vice versa. I mean, here are the conversion factors. I mean, I could just give you those factors, and I mean, you've seen those before. Maybe you already know them, but where is this idea coming from anyway? So I think it's important to see where it is. Well, so number one, let's consider two facts. Number one, that a whole revolution, one revolution around the circle is going to be 2 pi radians. Okay, that's what we are going to show. And we also know that one revolution is 360 degrees. All right, that's one revolution, which is going to be 2 pi radians. That's the end result, if we will. We also know that S equals 2 pi r. This is the formula to find the circumference of a circle. In other words, like the perimeter of the circle. Okay? So we're going to start with the arc length. Why are we going to start with the arc length? Because the arc length actually involves those radians we're looking for to define as degrees. Okay, so we know S equals to R theta from before. That's the formula for the arc length. But now I'm going to replace this S right here with what we get from here, which is 2 pi r. I'm going to replace that. That's 2 pi r equals R theta. All right? So let's see. How about we do some algebra and divide both sides by r? And careful, even though we can be potentially dividing by 0, in this case it's fine, because I mean there's no radius equal to 0. Radius equal to 0 is simply 1 point, which is the origin in this case. So dividing these two out, cancel out the r's, and that's a 2 pi equals to theta. Now the question is, what is this theta angle? I remember this theta angle was used to denote angles in center position. So because in this case we're considering the whole revolution, this angle theta equals 360 degrees. So that's where the 2 pi equals 360 degrees is coming from. And furthermore, if we treat this like an equation, we can reduce this to lowest terms by dividing both sides by 2. And what's that going to give us? Pi equals 180. 180, which is the same as saying, how about we divide both sides by 180. And that's going to give us pi over 180 degrees equals 1, which is 1 radian. Which is where these conversion formulas are coming from putting together the formula for the circumference of a circle and knowing the fact that one whole revolution gives 360 degrees. All right? So how about we do some calculations? But before that, let's briefly describe these conversion factors. So to convert from degrees to radians, multiply by pi and then divide by 180 degrees, and vice versa to convert from radians to degrees, multiply by 180 and divide by pi. Let's do a couple of examples to convert between one system and the other one. Okay, convert each angle in degrees to radians. Express in exact form, that is in terms of pi, and also round it to 2 decimal places. Okay, so to convert 60 degrees to radians, I mean, you can also think of like the stoichiometry, if you will, like those of you who are taking chemistry or are set to take it or already took a chemistry class, when we have something like, say, 30 grams of water, and we want to convert those to moles. So there's a couple of ways to convert them. That is 1 mole of water is that 18 grams? 18 grams of water, or 18 grams of water is equal to 1 mole of water. Then you will use the conversion factor that best works to cancel the units and obtain the desired unit. So for example, if I want to convert the grams to moles, which conversion factor do I use, the first one or the second one? Any ideas? Yes. The first one, because that actually cancels the grams and leaves us with moles, which are the desired units, right? So in the same way, if you're not sure what to multiply by and divide by, well, we want to cancel out the degree symbol, don't we? So we need to put that degree symbol where in the position that cancels, in this case 180 degrees, and that's 1, or rather pi radians. And well, that's going to be simply, so that cancels the degree symbol in the same way that we cancel grams and grams to obtain moles. And 60 divided by 180, I think that's pi over 3. All right? And they're also asking us to express this using decimals, and that's 1.05 radians. So this is fairly easy to find on the graphing calculator. Notice the pi symbol, where is that located at? It's located as the second function for the exponent right here. So we need to do second pi and then divided by 3. And that's 1.47, and rounding to 2 decimal places, yes, that's 1.05. Let's do the next one. Negative 45 degrees, so same. Divide by 180 degrees, multiply by pi, cancel the degree symbol, 45 over 180, I believe that's going to be pi over 4, which using our graphing calculator, that's going to give us, what's that? We're almost done. Negative pi over 4. Don't forget to keep carrying that negative symbol, negative sign. That's negative 0.79. And well, so these were nice numbers that go into 180 by some factor. We were able to reduce some factors like 180 was a multiple of 6. In the same way, 180 is a multiple of 45. However, there will be numbers that are not going to be nice numbers. Still, they multiply by pi and divide by 180. But in this case, 107 doesn't have any common factors with 180. So result, simply 107 pi over 180. So all we do is essentially is canceling the degree symbol, and that's about it. But of course, we want this using decimals. That's 1.87 radians. All right, and no need to write the word radians. Actually, recall that these angles in radians are unitless. We don't need to write anything else. How about we go the other way around, convert between radians and degrees? Well, so what we're going to do is do the same kind of stoichiometry problem, but in this case we want to cancel out that pi symbol and have that degree symbol to show up again. So in the previous case, we went by multiplying by pi and divide by 180, so now we're going to multiply by 180 and divide by pi. See how on the one hand the pi's cancel and we get back that degree symbol. All right, so multiplying, okay, we're actually the pi's cancel, and 180 divided by 6, is that 30 degrees? Well, since this number is just an integer, we don't need to do anything else to like find decimals. For letter B, same thing. Multiply by 180, divide by pi, divide out the pi's, and just do the indicated operation. So you could do 180 times 3 and then divide it by 4, or I would divide 180 by 4, which we already did, is 4 and then times 3. That's 135. Oh, hold on. (135 degrees), but don't forget the negative sign for it. And well, that's also an integer. No need to do anything on the calculator because of course it's not going to output anything for decimals. All right, there's other weird angles that are, I mean, they're just like a real number, like an integer. Well, these represent degrees whenever, I mean, these represent radians whenever you don't see the degree angle, but still, divide by 180, oh wait, no, multiply by 180 and divide by pi. And in this case, well, the exact answer will be 540 degrees over pi, but of course we want a decimal version of it, which in this case is going to give us 177.89. And let's do this on the graphing calculator. So that's 540 divided by second pi. That's our number. 171. Oh, wait. I got a different number, right? 171.89, not 177. 171.